All right, today we're going to be talking about acid-base titration, and particularly we're going to be looking at a strong acid being titrated with a strong base. So what I have here in this flask is 25 milliliters of 0.1 molar hydrochloric acid. Now I've also added about 3 drops of phenolphthalein solution, and that is an indicator solution that will indicate if something is an acid or a base. Now the way that works is that it is clear when it is an acid, and then once it's a base, it turns this pink color. So what we're going to do today is we're going to see the exact effects of an acid-base titration with that phenolphthalein indicator, and we're also going to look at what happens to the pH throughout this process. So before we get going and before we start a titration, I want to know, or I want to find out, what is the pH of this 0.1 molar HCl solution. So we've already been looking at strong acids and strong bases, and so if we just have a strong acid, the way in which we find the pH is we take the negative log of the concentration of that acid. So to find the pH before we get going inside of this flask, what we need to do is this. We need to take the negative log of the concentration of our acid, which is equal to the concentration of our H3O plus ions. So in that flask there is a 0.1 molar solution. So all I'm going to do to find out the pH is take the negative log of the 0.1 molar solution. So I'm going to plug that into my calculator, and I'm going to take the negative log of 0.1, press enter, and on my calculator I get the pH to equal exactly 1. Now what we're going to do is we're going to add some sodium hydroxide, and this sodium hydroxide that is in this burette is also 0.1 molar. So we're going to add it, and as we add it, I'm going to stop and pause and look at what is happening to the pH as we go through this process. So I'm going to erase this and then get started with our titration. So the basics of titrations. Like I said, we have that 0.1 molar solution of HCl, and we also have 0.1 molar NaOH, or sodium hydroxide, in this burette. So the first thing that I'm going to do is I'm going to add 1 milliliter of this NaOH, and then we're going to use the bore to look at what happens with the pH. So I'm going to, again, just add this very slowly, and just add 1 milliliter of this. So after 1 milliliter of NaOH that has been added to this flask, you can see that this flask is still clear. And because of the phenolphthalein indicator, a clear solution means that we're still on the acid side, or we have a pH below 7. Now we want to see what exactly is that pH, or what exactly happened as we added this 1 milliliter. So let's go to the board. The first thing that we need to look at is what exactly, or what type of chemical equation or chemical equilibria do we have to deal with? So the first thing that I'm going to do is just analyze or write down the two different solutions and what is exactly happening to them. So the first solution that we have there is aqueous hydrochloric acid, and in solution it breaks down into H plus ions and Cl minus ions. The other reaction that we have, or the other thing that's going on with this NaOH, is this. We have sodium hydroxide, which is aqueous, and it breaks down into Na plus ions and OH minus ions. Now what we're really interested in is what is exactly happening with our H plus ions from our hydrochloric acid that we started with as we add this sodium hydroxide or these sodium hydroxide ions. So the equation that we're most interested in is this. We have the H plus ions from that hydrochloric acid reacting with those OH minus ions, and what happens, because we're titrating a strong acid with a strong base, is that these come together and they form liquid water. So now we can finally get to, well, what is going to happen with the pH as we go through this process. So out to the side here, what we're going to have to do first is figure out how many moles of both H plus ions and OH minus ions do we have right at this point inside that flask. So out to the side here, I'm going to do a little calculation where we find the number of moles of H plus and we find the number of moles of OH minus. So out here, the first thing that we're going to do is we're going to find out how many moles of H plus do we have to work with. So what we are going to do is we are going to take the number of milliliters that we have. We're going to convert it to liters. So we had 25 milliliters of HCl. So that means we have 0.025 liters of HCl. And we're going to multiply this by the molarity. And the molarity of that HCl is 0.1 molar. And if we punch this into our calculator, we end up with 0.0025 moles of HCl. And ultimately, because HCl is a strong acid and it completely dissociates, we end up with 0.0025 moles of H plus. Now, I said a little while ago that we added exactly 1 milliliter of sodium hydroxide to this solution. And that sodium hydroxide was 0.1 molar as well. So, again, what we want to do is we want to find out the number of liters that we added, which that is 0.001 liters of this 0.1 molar acid. So again, I'm going to find out the number of moles of NaOH. So we punch that into our calculator, 0.001 times 0.1, and we end up with 0.0001 moles of sodium hydroxide. And again, because it's a strong base, we end up with 0.0001 moles of OH minus. So now we want to get down to what we started this problem with and get back to what we have here in our equation. And so what we have going on here is a couple of things. One thing that we have to think about is what happens as we add the NaOH. So I'm going to put together 3 categories up here on the board. And that's a before, how much NaOH we added, and then what is our final result, or what's left after that final result. So on this, what we're going to have is the before. We're going to have what we added. I'm going to leave that as our add. And then we're going to have our after effects. So before this whole thing started, before we added 1 milliliter of 0.1 molar NaOH, what we had was 0.0025 moles of H plus ions. So I'm going to go ahead and I'm going to add 0.0025 moles of this H plus ions. Now, what we added was 0.1 molar, or 1 milliliter of that 0.1 molar OH minus ions. So what I'm going to add to this column over here is this 0.001 moles of OH minus ions. And so now we have to get down to what is happening with the actual chemistry of this. So for the chemistry, you can see in the chemical equation, for each mole of OH minus that we have, it reacts with the same number of moles of H plus ions. So what happens is that 0.0001 moles of OH minus ions reacted with 0.0001 moles of H plus ions, and they combined together to produce 0.0001 moles of H2O moles. Now what we need to think about is, okay, what happens specifically to our H plus ions? Because ultimately that is going to indicate what our pH is. So what we need to do for this process is we need to take our number of moles of H plus and we need to subtract it from the number of moles of OH minus. So what I'm going to do here is a combination of our after effect. I am going to take 0.001 moles away from our original moles of acid. And what we get after the addition of this, because 0.001 moles of H plus ions reacted with those OH minus ions, what we end up getting after all of this has come about is our number of moles of H plus ions. So after all this process, we end up with 0.0024 moles of H plus ions. Now let's finally get back to that question we started with was, okay, well what effect did this pH, or what effect did this addition have on this pH? So what we're going to do is we're going to take this 0.0024 moles and we're going to need to plug it into molarity. We're going to need to find the molarity of this H plus ions and then plug it back into the pH equation. So we now need to think about what is our total number of milliliters of solution. We started out with 25 milliliters of that HCl and we added 1 milliliter of NaOH. So that gives us a total of 26 milliliters of solution. So what I'm going to do at this point, 0.0024 moles of H plus, is I'm going to divide it by our total number of liters of solution. So I'm going to divide this by 0.026 liters. And that's finally going to give us our concentration, or our molarity of H plus ions that remains. So when we punch this into our calculator, I end up getting 0.0923 molar of those H plus ions. So what I'm going to do is I'm going to plug into our pH equation our concentration of H plus ions. Let me go ahead and write that up and do this on my calculator. So when we punch this into our calculator, the pH is now at 1.03. Not much of an increase at all, but when you think about it, we haven't added much moles or much NaOH. So now what we're going to do, I'm going to leave this equation up because we're going to use it in the next couple calculations. What I'm going to do now is I'm going to add an additional 23 milliliters of NaOH, so that would bring our total up to 24 milliliters of NaOH to our solution that we already have here. Now, I'll stop occasionally and I'll stir it, and as I stir it, you'll start to see some pink start to appear. What that pink is starting to indicate is that we're having some base, some NaOH go into that solution, and it's starting to produce it or starting to raise the pH. Now, what happens with the indicator is this. At that equivalence point, this whole solution is going to turn pink, and I'll talk more about that once we get to that. So let me erase the board, and then we'll add an additional 23 milliliters of NaOH. Safety goggles back on, and I'm going to add again 23 milliliters of NaOH, and we're going to look at the board and see what happens to our pH after all this process goes on. And like I said, as I add it, you'll start to see these pink parts of the solution start to occur. Again, that's just the base reacting with the acid, and it's shown by that phenolphthalein indicator. As I swirl it, it goes back to a clear solution, and that indicates that it's still an acid in this solution. One more drop. Okay, so now I've added a total of 24 milliliters of NaOH. And so you can see this on the video, the solution is still clear. So what that indicates to us is that we still have an acid, so our pH when we calculate it should be below 7 still. And so let's go back to the board and let's do a similar thing that we just got done doing, by adding just 1 milliliter of NaOH, or sodium hydroxide. So again, we're going to go to our board, and the first thing that we're going to do is we're going to shift back over, and we're going to think about our moles of H plus that we added, or that we started out with, and our moles of NaOH that we added. So again, the number of moles of H plus has not changed. We still have 0.0025 moles of H plus. What has changed is how much OH minus, or NaOH, that we've added. So I'm going to go back to the board here, and I'm going to take the number of milliliters, convert it to liters, of the amount of NaOH that we've added. So we've added 0.024 liters of NaOH. Again, what I'm going to do is I'm going to multiply this 0.024 liters by the number of moles per liter, or molarity, of that NaOH. So I'm going to take 0.0024 times 0.1. And when you put that into your calculator, what you should get is 0.0024 moles of NaOH, which, because NaOH is a strong base, it completely dissociates. What we get is 0.0024 moles of OH minus. So now we're going to shift back to our equation, and we're going to look at, okay, what happened before with the addition, and ultimately with that addition, what effect does that have on our pH? So we're going to go back to this. We're going to have a before category. We're going to have that addition, and then we're going to see what happens after all that addition has occurred. So in this before category, again, the number of moles of H plus stays the same at 0.0025 moles of H plus. So we have 0.0025 moles of H plus acid before we began this whole experiment. The total amount of NaOH that we've added, and I'm saying total, I'm emphasizing that, is because we've added 24 milliliters total. So the total amount of NaOH that we've added up to this point means that we have 0.0024 moles of OH minus. So I'm going to put add 0.0024 moles of OH minus there. Now, again, we have to think about what exactly is happening with the chemistry of this reaction. So what is happening is this. We've added 0.0024 moles of OH minus ions, and those 0.0024 moles of OH minus ions are reacting with 0.0024 moles of H plus ions. Ultimately, those things, the OH minus ions that we've added, react with those 0.0024 moles of H plus ions, and they end up producing that water. They end up producing 0.0024 moles of H2O. And to find our pH, what we need to do is we need to subtract out how many moles of OH minus have reacted with our moles of H plus. So what I'm going to do is I'm going to just subtract the number of moles of OH minus from our H plus, and we're going to find out how many moles of H plus still are there in our solution right now. So if we take this calculation, and we will end up getting 0.0001 moles of H plus ions remaining. Now, as we did in the last one, moles of H plus isn't going to help us in that pH equation. What we need to do is we need to convert this to our molarity of H plus ions that we have in solution. So again, what we need to divide it by is the total number of milliliters in solution. So right now, in solution, we've added 24 milliliters to the already 25 milliliters of H plus, or hydrochloric acid. We have a total of 49 milliliters. So what we need to do to the number of moles of H plus is divide it by not 49 milliliters, but the conversion to liters, which is 0.049 liters. So we're going to divide 0.0001 by 0.049 liters to get our molarity. And so the molarity I end up getting is 0.002 molar H plus ions. And so what we're going to do to find the pH, the last part of this equation, is this. We are going to plug in the molarity of those H plus ions. So we're going to take the negative log of that molarity. And so when I punch that into my calculator and I round to 2 decimal places, I end up getting 2.70 as our pH. We are still very, very much an acid at this point in our solution. So now what I'm going to do is I'm going to again erase our equation here, and then we're going to go back to our experiment and look what happens at the equivalence point. So what I'm going to do now is I'm going to add 1 more milliliter of our sodium hydroxide in our burette, and I'm going to add that to our solution. And what's going to happen is a multitude of things. Number one, we're going to reach our equivalence point. And so what that means is that the number of moles of OH minus is equal to the number of moles of H plus. And so what we've seen through those couple calculations is that we have 0.0025 moles of H plus, or we began with that. So when I add this additional milliliter of NaOH, this will make our moles of NaOH equal to our moles of HCl, or H plus. So I'm going to add that, and then also once I add this, what's going to happen to my solution is that it is going to be a pink, a very, very faint pink color solution. What's happened there is the indicator has indicated to us that we have reached that equivalence point. So I am going to take some time to talk about that, and ultimately I'm going to talk about the pH of this solution. We don't need to do a big calculation for that. We can just talk about it. And then I'm going to add 1 additional milliliter of our sodium hydroxide. So let me first add just 1 milliliter of NaOH here. And I'm going to add this very, very slowly because, like I said, we are right at that equivalence point. And so a matter of 1 drop could reach our equivalence point. And that pink portion I talked about is staying in solution a lot longer. Again, what we're looking for is a pink solution to stay throughout even after we stir this. Okay. I think we are there. So it happened very, very quickly. I almost missed it. Wasn't paying attention to it. And so what you can see is it's very, very faint pink. And that's exactly what we want. Oh, it did not go pink. So it's very, very close to the equivalence point. What happened there is as I stirred it up, that acid reacted with that sodium hydroxide and went back clear. So if this happens, all you need to do is you need to go put the flask underneath the burette and add just 1 drop, because that's probably all it's going to take, of this sodium hydroxide. So I'll be very careful here. And there's 1 drop. And I'm going to stir it up. Make sure we don't go pink. So we have reached that pink, which is good. It's a little bit darker than I would like it. But what this has meant is that I have that 1 drop. And as I stir it, just to make sure we are at that equivalence point, it's not going back clear. So what this means is that we have reached our equivalence point. And so what happens here, what has happened here, the chemistry side of things, is this. The number of moles of H+, which was 0.0025, we've calculated that over and over, is equal to the number of moles of OH- ions. So we have added exactly 0.0025 moles of OH- ions. So what this means is right when this solution turned pink, we have a couple things that are happening. 1, we've reached that equivalence point, and 2, what that means is that because we titrated a strong acid with a strong base, we have not only reached the equivalence point, but gone to a pH of 7. So if you think about the chemistry, all of the H+ ions have reacted with all of the OH- ions. They produce a pH of 7, and ultimately right now, that solution is neutralized at a pH of 7. So, quick takeaway from here, at the equivalence point, moles of acid and base are equal, and because we titrated a strong acid with a strong base, the number of, or the pH in this instance, is at 7. So now what I'm going to do is I'm going to go 1 step past the equivalence point. And I'm going to add an additional milliliter of NaOH. When I do this, again, we'll look at the solution, and we'll go back to calculating, well, what is the pH now if I just add 1 additional milliliter to this solution. So let me go ahead and add 1 milliliter to this solution. All right, so at this point, what has happened? I don't know if you can see it in the video, but my solution has got considerably darker pink. What that indicates to us is that we are most definitely now a base based on what the phenolphthalein indicator does or indicates. So we are very, very much a base. And now what I want to do is I want to see, well, what exactly is our pH in this instance. So what we're going to do is we're going to go back to our equation here, or our number of moles here, and we're going to think about this. We have a couple of things that have happened. 1, we still have the same number of moles of H+. That has not changed throughout this whole process. We're still at 0.0025 moles of H+. However, like I said, I went 1 milliliter past that equivalence point. That means I added a total of 26 milliliters of NaOH. So what I'm going to do is I'm going to take our number of milliliters, convert it to liters, which it's 0.0 0.026 liters, and I'm going to multiply it by the number of moles of NaOH, or the molarity of NaOH, which is 0.1 molar. So when I do this, when I go through the calculation, the number of moles of NaOH and ultimately the number of moles of OH minus is 0.0026 moles of OH minus. So now we're going to go back to our before and addition and after chart, and we're going to calculate what is my pH in this instance. So again, I'm going to start with our before picture, before we added any NaOH. And so before that happened, we had 0.0025 moles of H+. Now what has happened is that we have added 0.0026 moles of OH minus. We have an addition of 0.0026 moles of OH minus. And now we need to think about the chemistry of all of this happening here. We can only react the number of H plus moles with the equal number of OH minus moles. So that means that we can only react 0.0025 moles of H plus with 0.0025 moles of OH minus. If we go over this number right here in this instance, this means that we now have leftover OH minus. We now have leftover base. So what I'm going to do is I'm going to subtract the total number of moles of H plus ions, and I'm going to find out how much OH minus is left over. So what I'm going to do is take 0.0026 moles of OH minus and subtract it from the number of moles of H plus ions that it's reacted with. So when I do this, what I end up getting, the number of moles of OH minus left over after we've gone past that equivalence point, is this. .0001 moles of OH minus moles exist after we have gone through this. Remember, all of the H plus has reacted with that OH minus, and we still have leftover OH minus. So we end up with 0.001 moles of OH minus. Now to find the pH, we need to find the total molarity of OH minus. So think what happens. We have, or we started with 25 milliliters of HCl, and now we've added 26 milliliters of NaOH. So what we need to do is divide it by the total, or we need to take that 0.001 moles and divide it by the total liters of solution. So again, we had 26 milliliters of NaOH added to 25 milliliters of HCl. That gives us a total of 51 milliliters, but our molarity equation states that we need our solution in liters, so that is 0.051 liters. And so when we punch this into our calculator, 0.001 divided by 0.051 liters, we end up with a molarity of 0.0196. Now, this is our molarity of OH minus. So what we can do with our molarity of OH minus is we can put it into the POH formula. And now the POH formula is the same formula we use for pH. with the exception of have a strong base, or the number of molarity or concentration of OH minus. So the POH in this case is going to be the negative log of our 0.0196 molar OH minus. So I'm going to plug this into our calculator. And I end up with a pH, or excuse me, POH of 1.71. And to find our pH, what we're going to do is we're going to take 14 equals our pH, which we don't know yet, plus our POH, which we found out was just 1.71. We subtract 1.71 from each side, and we end up with a pH of 12.29. So, in a matter of 2 milliliters of NaOH, of that 0.1 molar NaOH, we've gone from a pH of around 2 to now we're at a pH of 12.3. So that concludes this video on a strong acid, strong base titration. Thank you.